we present ManiWAV, a robotic system that learns manipulation skills from in-the-wild audiovisual data. Audio signals reveal rich information about the interactions and object properties. How can we leverage audio feedback to learn context-rich manipulation skills? We propose a data collection and policy learning framework to learn robot manipulation from both vision and audio feedback. The data collection device is a handheld gripper that allows humans to demonstrate a manipulation task in the wild with natural haptic feedback. For each demonstration, the vision data is captured by a GoPro camera with fisheye lens, and the audio data is captured by a contact microphone embedded inside the gripper finger. The audio data is stored synchronously with the vision data into an MP4 file through the external mic port of the camera. We directly learn robot manipulation policy from the human demonstration data. Here's an example human demonstration with audio-visual feedback. One key challenge for learning the policy is the audio domain gap due to robot motor noises and other robot interaction noises generated during deployment time, which is out of distribution for the training data. To address this challenge, we apply an audio data augmentation technique, where we randomly sample noises from a collection of recorded robot noises and the ESC50 audio dataset, and overlay the noises to the original signal. We found this approach allows the model to focus on the task-relevant signals and ignore the unpredictable noises, yielding more robust robot behaviors during test time. The sensory motor learning model takes in fisheye images and augmented audio data converted into a log-mouth spectrogram. The image and audio data are encoded by a Clipper-trained VIT encoder and an audio spectrogram transformer encoder respectively. The encodings are then fused through an additional layer of transformer encoder to obtain the final audio-visual representation. This representation is concatenated with the history and effector poses and passed as global condition to a diffusion policy head. We demonstrate the capability of our system on 4 context-rich manipulation tasks, including wiping shape from the whiteboard, flipping bagel with spatula, pouring objects from the cup, and strapping wires with Velcro tape. We also collect in-the-wild bagel flipping demonstrations in diverse environments using our proposed data collection device. We found that the policy trained on in-the-wild demonstrations is able to generalize to unseen in-the-wild environments, whereas the policy trained on demonstrations collected only in the lab fails to generalize to the new environment. By leveraging audio feedback, our policy is able to infer context and correctly insert the spatula between the bagel and the pan, whereas the policy trained with only vision data pokes on the side of the bagel. In the wiping task, the robot is supposed to wipe the drawing completely from the whiteboard. The challenge of the task is that the robot needs to maintain contact with the whiteboard while following the shape. The policy trained with our method is able to reliably wipe the shape off from the whiteboard by leveraging audio feedback to infer whether the eraser is in contact with the whiteboard or not. The policy also zero-shot generalizes to unseen table height. Unseen shape, such as a star. Or unseen eraser with different wiping surface. On the other hand, the vision-only baseline usually results in a policy that floats above the board. A baseline that uses MLP layers instead of transformer encoder to fuse the vision and audio features result in unexpected behaviors such as early termination before the shape is completely wiped off. The baseline that does not use noise augmentation on the audio data during training often yields unsafe behavior by exerting too much force on the whiteboard that causes the gripper to press into the board. In this task, the robot is supposed to flip a bagel in a pan from facing down to facing upward using a spatula. As we can see, the policy trained with our method is able to successfully complete the task by inserting the spatula between the bagel and the pan, and starting to tilt up the spatula after the bagel is in contact with the edge of the pan. Our policy also generalizes to unseen table height. Our policy is also robust against background noises. As for baselines, the vision-only policy fails by either poking on the side of the bagel or loses contact with the bagel early before it can be flipped. The policy trained with a ResNet 18 audio encoder often yields a failure case when the robot keeps moving downward after the spatula hits the bottom of the pan, causing the spatula to displace. The policy trained with an MLP policy head instead of a diffusion policy head also has the problem of losing contact with the bagel early. In the pouring task, the robot is supposed to grasp the white cup, pour all objects inside to the pink cup, and place the white cup on the table. The challenge is that the robot cannot see inside the cup given limited view and must infer whether the cup is empty or not from the vibrations of objects inside the cup. By leveraging audio feedback, our policy is able to correctly infer whether there are objects inside the cup or not, and pour when there are objects or place the cup on the table if the cup is empty. Our policy also generalizes to auto-distribution number of dice, such as an empty cup. Or more number of dice than the training distribution. We found that the policy also generalizes to objects that generate similar sounds, such as screws. On the other hand, the vision-only policy either never executes the pour action or misses the target and never executes the place action. We also play with different lengths of audio history that is input to the model. With 1 second audio history, the shortened audio window does not contain sufficient information to guide robot actions. As a result, the common failure case is that the policy never executes the place action after pouring. And with 10-second audio history, one representative failure case is that the robot places the cup directly without pouring. In this task, the robot is supposed to choose the hook tape from a few randomly placed tapes that can be either loop or hook, and strap wires by attaching the hook tape to the loop tape underneath the wires. The hook and loop tape has different surface materials and only the hook side can attach to the loop side. By leveraging audio to sense the subtle surface material difference, our method is able to choose the correct hook tape and attach it on top of the wires. On the other hand, the vision-only policy makes random decision as the difference in the tapes are not observable from vision. As a result, the policy picks up the wrong tape. For more information such as the code and dataset, please visit the project website. Thank you.